Next problem. In the loop shown, the magnetic induction at the point O is. Now look at the diagram. They have given the two loops and the direction of the currents are given and their radii are given. One is R1 and another one is R2. You have to calculate what is the magnetic induction at the point O. Options: A, mu naught I into R1 plus R2 divided by 8 into R1 R2. B, mu naught I R1 R2 divided by 8 into R1 plus R2. C, 0. D, mu naught I into R1 minus R2 divided by 8 into R1 plus R1 R2. Now look here in the diagram. Now they have given a loop which is having two straight portions and two curved portions. The straight portions are along the line joining the point to the current element. Therefore angle is 0. Therefore there is no contribution of magnetic field from the straight portions in this case. The curved portions are going to contribute for the magnetic field at the point O. Now we know that in the case of a curved, that is circular coil, the magnetic field at its center is given by B is equal to mu naught I divided by 2R. This is for one circular coil, complete circular coil. Now if you take only a portion of the circular coil or an arc, then that formula becomes B is equal to mu naught I divided by 2R multiplied by theta, angle of the arc divided by 2 pi. Now that is the formula. Magnetic field due to the circular arc, theta B is equal to mu naught I divided by 2R into theta by 2 pi. Now take the first arc of radius R1. The angle subtended is obviously 90 degree, that is pi by 2. Therefore I will take B1 is equal to mu naught I divided by 2, radius is R1 into theta here pi by 2 divided by 2 pi. Now pi get cancels. Therefore I will get mu naught I divided by 8R in R1, 8R1 in the denominator. Now similarly for the second loop, which is also circular arc, but radius is R2. Therefore obviously B2 is also the same, mu naught I divided by 2R2 into angle is same 90 degree, pi by 2 divided by 2 pi. Now pi get cancels. Therefore I will get B2 is equal to mu naught I divided by here I divided by 8R2. Now look at the direction of the magnetic field. Since the current is in clockwise direction, the magnetic fields are into the plane of the paper according to the right hand rule. Okay. So B1 is also into the plane of the paper and B2 is also into the plane of the paper. Therefore total magnetic field is the sum of the two, B1 plus B2. So therefore mu naught I divided by 8 is common. If I take it out, it is 1 by R1 plus 1 by R2. Now taking the LCM and simplifying, I will get mu naught I divided by 8 into R1 plus R2 divided by R1 R2. Hence A is the right answer here. Clear? Next problem. Magnetic field at a distance r from an infinite long straight conductor carrying a steady current varies as. Options: A 1 by r, B 1 by r square, C 1 by root r and D 1 by r cube. Now here they have given an infinite straight conductor. The magnetic field at a certain distance r from the infinite straight conductor, we have the formula. So B is equal to mu naught I divided by 2 pi r. Now that is the formula. Therefore here the magnetic field is inversely proportional to the distance. Therefore B proportional to 1 upon r, B proportional to 1 upon r, and hence A is the right answer. It is a conceptual problem. So B proportional to 1 upon r, inversely proportional to the distance from the infinitely long straight conductor. Next problem. A straight current carrying conductor is kept along the axis of a circular loop. A straight current carrying conductor is kept along the axis of a circular loop carrying current. The force exerted by the straight conductor on the loop is. Options: in the plane of the loop away from the center, B in the plane of the loop towards the center, C 0, D perpendicular to the plane of the loop. Now carefully look here, there is a circular loop which is carrying the current. Because of the circular loop, we are having a straight magnetic field at the center. The magnetic field is along the axis of the circular loop. Now along the axis of the circular loop, we are placing a current carrying conductor. So therefore, the conductor and the magnetic field from the circular loop, they are parallel to each other. Since they are parallel, the magnetic force is obviously 0. Clear? Now that will be shown by this animation diagram. Now we have a circular loop in which the current is moving in the circular path. Now we are placing a current carrying conductor at the axis of the circular loop. Now because of the circular current in the coil, there is a magnetic field around it. Now this magnetic field is that blue lines, they are representing the magnetic field due to the current carrying straight conductor. Now here asked force exerted by the straight conductor on the loop. Now what is the force on the loop we have to calculate. Now on the loop, the direction of the current and the direction of the magnetic field, they are parallel to each other, and hence theta is 0, sin theta is also 0. Therefore, the magnetic force is 0. Therefore, C is the right answer. Now, formula F is equal to I into L in B, ILB sin theta. Now, here theta is 0, therefore sin 0 is 0, and hence the force is 0. C is the right answer here. Move on to the next problem. The deflection in a moving coil galvanometer is reduced to half when it is shunted with a 40 ohm coil. The resistance of the galvanometer is, we have to calculate it. Now options A 15 ohm, B 20 ohm, C 40 ohm, and D 80 ohm. Now simply look at that. This is a theoretical concept. There is a moving coil galvanometer. It is showing certain deflection. Now its deflection is reduced to half by shunting a 40 ohm resistor. When the deflection is reduced to half, it is possible only when the current flowing through the shunt resistor and the current flowing through the coil, that galvanometer, should be exactly equal, that is reduced to half. This is possible only when the value of the shunt resistor and the value of the resistance of the galvanometer both are equal. On this theoretical concept, answer is C is the right answer. Now we look at that animated diagram here. Now here we have a cell which is connected to a galvanometer, and obviously there is a current flowing through that galvanometer. Assume that this amount of current is flowing. Now galvanometer is showing full scale deflection here. Assume that. Okay. Now we are connecting a shunt resistor of 40 ohm is connected across it. As and when the shunt resistor is connected, the current divides at the junction. Now half of the current is passing through the galvanometer and the remaining half is passing through the 40 ohm shunt resistor as shown in that diagram. Now this is possible that current is equally divided only when the resistance of the galvanometer is exactly equal to the resistance of the shunt resistor. On this theoretical concept, we can say that resistance of the galvanometer is 40 ohm, therefore C is the right answer here. Clear? Next problem. A neutron, proton, electron and alpha particle enter a region of uniform magnetic field with the same velocities. Velocities are same. The magnetic field is perpendicular and directed into the plane of the paper. The tracks of the particles are labeled in the figure. The electron follows the track. Now here they have given 4 particles, that is a neutron, proton, electron and an alpha particle. And they are passing perpendicularly in a uniform magnetic field with the same velocity. Since the velocity of the charged particles is perpendicular to the magnetic field, they obviously experience magnetic force. Now we have to find out what is the track of the electron. Options A is D, B is C, and option C is B, and option D it is A. Now carefully look at the given 4 particles. Among the 4 particles, neutron is electrically neutral, therefore it will not experience any magnetic force because it is uncharged, therefore it moves straight, therefore C. Now remaining 3 particles, electron is negatively charged, proton and alpha particle are positively charged. Since proton and alpha particles are positively charged, now these 2 particles they deflect on one side. Now in the diagram they are deflecting towards the left, that is A and B obviously represents one is proton and another one is the alpha particle obviously. And the remaining one is D, that is electron, which is deflected towards the right side. So obviously D is the path, therefore answer A, here answer A which is D, it is the right answer. Now we look at the animated diagram here. Now we have 4 particles. First is neutron, which is electrically neutral. Therefore in the presence of an external magnetic field, it will not experience any magnetic force, therefore it is moving straight away. Now consider the proton. Since the proton is positively charged, it is to be deflected towards the left as shown in the diagram. Now it experiences a force towards the westward, since the velocity is upward and the magnetic field is into the plane of the paper, and applying Fleming's left hand rule, it is going to experience a force towards the west direction, that is left. Now consider the another particle, that is alpha particle, which is represented as A. Since it is also positively charged, it is going to describe a circular path. It is also deflected towards the left as shown in that animated diagram here. Now the 4th particle left is electron, which is negatively charged. Since electron is negatively charged, it is going to be deflected in the opposite direction of the protons and the alpha particle. Now that yellow ball represents the electron, which is deflected towards the right. Therefore answer is D is the deflection path, but in the answer it is A answer is given, that is A, that is path represented by D is the path of the electron. Electron follows the path D. Like this we can easily analyze that one. Therefore D is the right answer here. That means A is the right answer, that is D is the path of the electron. Don't get confused here. Okay. Next problem. A particle of charge E and mass m moves with a velocity v in a magnetic field capital B applied perpendicular to the motion of the particle. The radius r of its path in the field is given by. Now it is a simple conceptual problem. Here we have to write what is the expression for the radius. Now options A, b into r divided by E into m, B, EV divided by B into m, C, BE divided by m into V, and D, m into V divided by B into E. Now whenever a charged particle moves in the presence of a magnetic field perpendicular to it with a certain velocity, it describes a circular path, and the radius of the path is given by mv divided by q into b, where q is the charge. Now here charge is given, q is equal to E. Therefore it is mv divided by E into b or b into E. So therefore D is the right answer here. Simple problem. Next problem. The torque required to hold a small circular coil of 10 turns, area 1 mm square, and carrying a current of 21 divided by 44 amps. In the middle of a long solenoid of 10 to the power of 3 turns per meter, carrying a current of 2.5 amps, with its axis perpendicular to the axis of the solenoid. Options. Now look at the diagram. We have a solenoid here. Inside the solenoid, a circular ring is placed such that plane of the circular coil is perpendicular to axis of the circular coil. Axis of the circular coil is perpendicular to axis of the solenoid. Axis of the solenoid. Now options are now A 1.5 into 10 to 9 Newton meter, B 1.5 into 10 to minus 9 Newton meter, C 1.5 into 10 to minus 8 Newton meter, D 1.5 into 10 to minus 6 Newton meter. Now in this diagram we have a solenoid. Because of the solenoid there is a magnetic field at the center. That magnetic field B is given by mu naught into small n into I. In the presence of the magnetic field we are placing a current carrying loop such that the axis of the loop is perpendicular to the plane of the perpendicular to the magnetic field produced by the solenoid. Now axis of the loop, since it is carrying a current, therefore it possesses a magnetic moment. Now we have to calculate what is the torque. We know that torque is given by tau is equal to m cross b or m into b into sin theta, that we know. Here what is m? It is the magnetic moment of the circular loop which is carrying the current. B, it is the magnetic field due to the solenoid, and theta is the angle between the two. Theta is given, it is perpendicular, that is 90. So therefore m is magnetic moment is given by the formula n into I into A. N is the number of turns in the coil, I current flowing through the coil, and A is area of cross section of the coil. And what is the magnetic field due to the solenoid? That is mu naught small n into I, where n is number of turns per instant, that we know. Sin theta is sin 90, it is 1. Now substituting the values, now n is number of turns in the coil 10, and the current flowing is 21 divided by 44 amps into, and area of cross section is given 1 into 10 is to minus 6. And 4 mu naught is 4 pi into 10 to minus 7, and number of turns is given 10 to the power of 3 into current flowing in this solenoid is 2.5. Now just replace pi divided by 22 by 7, that is easy for the calculation. I am replacing pi divided by 22 by 7. Now look here, and 22 2s are 44 get cancels, and 7 1s are, and 7 3s are 21 get cancels. Now 2 1s are 2 4s are, that cancel. Now we left with 3 into 2, that is 6. 6 into 2.5, it is 15. So 15 into 10 is to minus 5, 10 is to minus 7, 10 is to minus 12 into 10 is to 3, it is 10 is to minus 9. 15 into 10 is to minus 9 or 1.5 into 10 is to minus 8, that is the torque. Therefore 1.5 into 10 is to minus 8 Newton meter, it is the answer, and hence the answer is C. C is the right answer. 1.5 into 10 is to minus 8 Newton meter. Next problem. A current I is flowing through the loop. The direction of the current and the shape of the loop are as shown in the figure. The magnetic field at the center of the loop is mu naught I divided by R times. We have to calculate the coefficient. Now look at the diagram. They have given the current loops. So one loop is 3/4 of the complete circle, and another loop is 1/4 of the complete circle. That is arc. Arc of length 3/4 times, and another arc of length 1/4 times. Now MA, it is the radius of the larger arc, that is taken as, it is given capital R. MB, it is radius of the smaller arc, it is given 2R, and the angle is given 90 degree. Now look here, we are having two arcs and two straight parts. The straight parts are along the line joining the current element to the point O, and hence these straight parts will not contribute for the magnetic field because angle is 0, sin 0 is 0. Clear? Only the circular parts are going to contribute for the magnetic field at the point M. We look at the options. Now A 7 by 16 but into the plane of the paper, B 7 by 16 but out of the plane of the paper, C 5 by 16 but into the plane of the paper, and D 5 by 16 but out of the plane of the paper. Now before going to find the coefficient, by the method of elimination, we can remove easily the two answers from these two. How? Now look at the direction of the current. In the two arcs, the current is in the clockwise direction. Since current is clockwise, what is the direction of the magnetic field given by the right hand rule? It is into the plane of the paper. Therefore, answer should have into the plane of the paper. Therefore, we can eliminate B and D because the direction of the field is but out of the plane of the paper. Hence, we can remove B and D. Now, we have to choose A, either A or C. Now, we will work out the coefficient. Now, for the first arc, larger arc, it is given magnetic field due to a circular arc is given by B is equal to mu naught I divided by 2 pi to mu naught I divided by 2 r into theta by 2 pi. So, here theta is, it is the angle subtended by that arc. Now, look at the larger one, it subtends an angle of 270 degree, that is subtends an angle of 270 degree, that is 3 pi by 2. 270 means it is 3 pi by 2. So therefore magnetic field due to the larger loop is V1 if I take mu naught I divided by 2 into its radius is r into angle is 3 pi by 2 divided by 2 pi. Now pi get cancels here. So 3 mu naught I divided by 8 r here. 3 mu naught I divided by 8 r. Now for the second arc, the current is same. Only thing is arc subtends an angle of 90 degree, that is pi by 2, and its radius is 2r. Therefore, B2 is equal to mu naught I divided by 2 into 2r, pi by 2 into 2 pi. Now pi get cancels, therefore I will get mu naught I divided by 16r. Mu naught I divided by 16r. Since the current is in clockwise direction, the field is into the plane of the paper, therefore the two fields gets added up. Therefore total field is equal to B1 plus B2. Now mu naught I divided by r is common, 3 by 8 plus 1 by 16. Now in the denominator, 16 is the LCM. So 8 2s are 2 3s are 6 plus 1. Therefore I will get 7 by 16. Therefore coefficient is 7 by 16, and hence the answer A is the right answer.
Next problem. A horizontal metal wire is carrying an electric current from north to south. Using a uniform magnetic field, it is prevented from falling under gravity. The direction of this magnetic field should be towards. Now here there is a metal wire which is carrying a current from north to south direction. Now it is prevented from falling down under gravity. That means it is suspended in mid-air. Now gravity is pulling downwards, and there is an upward magnetic force. The direction of the magnetic field they have asked. Okay, option west, option A west, B east, C south, and D north. Now look here, there is a wire which is carrying current from north to south. By using a right hand clasp rule, we get the direction of the magnetic field. Above the wire it is towards west, and below the wire it is towards east. Below the wire means we are under the wire, and hence for us the direction of the magnetic field is towards east. Now that can be shown with the help of a simple this animation. We have a person standing below an electric wire which is carrying the current from north to south direction. Now upper part is north and downwards it is south. Obviously there is a magnetic field around it. Now that circular loop gives the direction of the magnetic field. Now it is given by the right hand rule. Therefore in the upper part the magnetic field is towards the west, and in the lower part the magnetic field is towards the east direction as shown by that arrow mark. And hence the answer is B, that is east direction. Magnetic field is east direction. Next one. The maximum potential that can be measured with a voltmeter of resistance 1000 ohm is 6 volts. Resistance that must be connected to measure a potential of 30 volts with it is options A 4000 ohms in series, B 6000 ohms in series, and C 12,000 ohms in series, and D 2000 ohms in series. Now from the data, first they have given the maximum potential that can be measured is 6 volts with the help of a resistance of 1000 ohms. Now we can calculate Ig, the maximum current flowing through the current for full deflection. That is Ig is given by V by Rg. Now V is 6 volts divided by 1000. Now 6 by 1000 is 6 into 10 to minus 3 amps or 6 milliamps here. Okay, that is the current. Now here we have to connect an additional resistance so that it can measure a higher voltage of 30 volts. Okay. Therefore, the resistance to be connected R is equal to V by Ig minus Rg, where Rg is the resistance of the galvanometer. That is given, that is voltmeter here. Now, we have to measure a maximum voltage of 30 divided by the current is 6 into 10 raised to minus 3 minus of 1000 ohm. It is the resistance of the initial case of the voltmeter. Now, 30 by 6, it is 5. 5 into 10 raised to minus 3 is in the denominator. If I take it to the numerator, it is plus 3. So 5 into 10 to the power of 3, that is 5000 minus 1000, it is 4000. It has to be connected in series. Hence, A is the right answer here. Okay, very simple problem. Move on to the next problem here. A maximum current of 0.5 milliamps can be passed through a galvanometer of resistance 20 ohm. The resistance to be connected in series to convert it into a voltmeter of range 0 to 5 volts. Now here the options are A 980 ohm, B 9980 ohms, C 990 ohms, and D 9990 ohms. Now in this problem, a galvanometer has to be converted into a voltmeter. Now this can be done by connecting a high resistance in series. We know the value of high resistance, R is equal to V by Ig minus Rg formula. Now V, the voltage maximum range is volts, and Ig is 0.5 milliamps. That is 5 divided by 0.5 milli, it is 10 raised to minus 3 minus of resistance of the galvanometer, it is 20. Now 5 by 0.5, it is 10, and in the denominator we have 10 raised to minus 3. If it moves to the numerator, it becomes 10 to the power of plus 3. Now 10 into 10 to the power of plus 3 is 1000. 10 into 1000 is 10,000. Therefore it is 10,000 minus 20. 10,000 minus 20 is 9,980 ohms. It is to be connected in series. Hence B is the right answer here. Okay. Move on to the next problem. A galvanometer of coil resistance 100 ohm is connected to a shunt resistance of 10 ohm. The current through the galvanometer is I1, the current through the shunt is I2, and the total current into the combination is I3. Then the ratio of I1 is to I2 is to I3. Options A 1 is to 10 is to 11, B 10 is to 1 is to 11, C 11 is to 10 is to 1, D 10 is to 11 is to 1. Now here the current flowing through the galvanometer is taken as I1 and current flowing through the shunt is taken as I2 and their sum is I3. Now we know that the current and resistors should be in the inverse ratio. The current flowing through the galvanometer and the shunt should be in the inverse ratio of their resistance. Therefore, I1 is to I2, it should be is equal to R2 is to R1. Now, I1 is to I2 is equal to, now shunt resistance R2, that is 10 ohm, and the resistance of the galvanometer, it is 100 ohm. Therefore, the ratio of I1 is to I2 becomes 1 is to 10. But I1 plus I2 is 11. Therefore, I1 is to I2 is to I3 becomes 1 is to 10 is to 11. Hence, A is the right answer here. Move on to the next problem here. A galvanometer has a resistance of 400 ohm. The value of the shunt shows that its sensitivity is to be reduced by 1 by 50 times. Sensitivity has to be reduced by 1 by 50 times. The options: A 6.16 ohm, B 7.16 ohm, C 8.16 ohm and D 9.16 ohm. Now we know the value of, we know the expression for the shunt resistance in the case of a galvanometer converting into ammeter, that is Rs is equal to Ig into Rg divided by I minus Ig. Now here the sensitivity has to be reduced. That means Ig by I should be 1 by 50. That has to be reduced. Now in the formula we divide both numerator and denominator by Ig. So we will get Rg divided by I by Ig minus 1. But Ig by Ig is 1 by 50. I by Ig is 50. Now simply substitute the values. So Rg it is 400 resistance of the galvanometer. I by Ig becomes 50 minus 1, that is 400 divided by 49. So 400 divided by 49, if I assume 49 is 50, so 400 by 50 becomes, it is around 8. Therefore answer should be 8.16 ohms. Hence C is the right answer here. Next problem. Resistance of a moving coil galvanometer is 5 ohm. The maximum current it can measure is 0.015 amps. To convert it into an ammeter to measure 1.5 amps. What you have to do? Options: connect 5 by 99 ohms in series. B. Connect 99 by 5 ohms in parallel. C. Connect 5 by 99 ohms in parallel, and D. Connect 99 by 50 ohm in series. Now here we are converting the galvanometer into ammeter. Therefore the resistance has to be connected in parallel. Obviously choice A and D are eliminated because they are in series. The answer should be between B and C. Now we will work out which is the correct answer. Now the same by elimination method we have removed A and D. Okay. Next we have the shunt resistance Rs is equal to Ig into Rg divided by I minus Ig. Now substituting the values, they are given. Ig is given 0.015 amps and Rg is 5 ohms given, divided by main current, it is 1.5 minus 0.015. Now in the denominator we have 1.485 after subtraction. Now if you remove the decimals, I will get 15 into 5 divided by 1485. 15 into 5 divided by 1485. Now 15 ones are 15 nines are 135. In 149 we are having 13. Therefore once again it is nines. So in the denominator I will get 99. In the numerator I will get 5. Therefore Rs should be equal to 5 by 99 ohms. It is to be connected in parallel. Therefore C is the right answer here. Next problem. A rectangular coil of wire of 500 tons and area 10 into 5 centimeter square carries a current of 2 amps in a magnetic field of 2 into 10 to minus 3 Tesla. If the plane of the coil is parallel to the field, plane of the coil, look here, this sentence is very, very important. Plane of the coil is parallel to the field. The torque on the coil is, so options A 0.1 Newton meter, B 0.01 Newton meter, C 0.001 Newton meter, D 1 Newton meter. Now in this problem, a rectangular coil having 500 tons and area of cross section is given. The area of cross section is in centimeter square. We have to convert it into meter. That should be remembered. And the magnetic field and the plane of the coil are parallel. Now look here, since they have given parallel, that is parallel, we think that the angle theta is 0. But in the case of a torque, the angle is between the magnetic moment and the field vector. Since the plane is parallel, what is the direction of the magnetic moment? Magnetic moment is always perpendicular to the plane. You should remember this point very, very clearly. Here theta is angle between the direction of the magnetic moment, which is perpendicular to the plane, and field and magnetic moment are perpendicular. Therefore theta is 90 degree here. You have to choose. Okay, that point is very, very clear. Now we have torque is given by mb sin theta. Even though they have given parallel, we think that theta is equal to 0. Therefore obviously the answer becomes 0. But it is wrong. Here theta is the angle between the magnetic moment, whose direction is perpendicular to the plane of the coil, and the direction of the field. Now m is n into I into a magnetic moment, and field is given, and sin theta. Now m number of tons is given 500 tons and area is 10 into 5 centimeter square. It has to be converted into meter square. Therefore it is 10 raised to minus 2 whole square. It becomes 10 raised to minus 4 and multiplied by the magnetic field 2 into 10 raised to minus 3. Now carefully simplify here. 500 into 2, it becomes 1000 into 10, it is 10,000. 10,000 can be written as 10 to the power of plus 4. Now here we have 10 to the power of minus 4, it cancels. The remaining thing is 5 into 2, it is 10. 10 into 10 raised to minus 3, or it becomes 10 raised to 1 into 10 raised to minus 2, or 0.01 Newton meter. So therefore it is B is the right answer here. Next problem. Magnetic field at the center of a circular loop of area pi meter square is 0.1. The magnetic moment of the loop is, the magnetic field is given, we have to calculate the magnetic moment. Now options 0.1 pi divided by mu naught, B 0.2 pi divided by mu naught, C 0.3 pi divided by mu naught, D 0.4 pi divided by mu naught. The magnetic field is given at the center 0.1 Tesla. We have to calculate the magnetic moment of the loop. The magnetic field due to a circular loop is given by mu naught I divided by 2r. Mu naught I divided by 2r. Now here radius is not given. First we have to calculate the current from this expression. Because they have given the magnetic field, first we have to find what is the current flowing through that circular loop. Therefore, from this expression, current I is given by 2Br divided by mu naught. It is one expression. Now, magnetic moment is equal to I into A. Now, substitute for I, that is 2Br divided by mu naught. And area, it is given pi r square. Or simply, the area is given, value is pi meter square. They directly have given. From the area, we have to calculate the radius, that is pi r square is equal to pi. Now pi get cancels, therefore r square is equal to 1, therefore r is equal to 1 meter. Now substituting all these values, 2 into magnetic field is given 0.1 and r we have got 1 divided by mu naught into pi. 2 into 0.1, it is 0.2 pi divided by mu naught, hence B is the right answer here. Next problem. Two straight parallel wires carry currents of 200 milliamps and 1 amps in opposite directions. They are carrying the currents in opposite direction here. Okay. If the wires are 20 centimeter apart, the distance of the neutral point from the 1 ampere wire is options 5 centimeter A, B 15 centimeter, C 20 centimeter and D 25 centimeter. Okay, so without solving this one by simply a theoretical concept, we can easily work out what is the value of this one. Now, since the currents are in opposite direction, therefore the point, it should be outside, point should be outside the two conductors. And one more thing, since they have asked to find what is the distance from the 1 ampere wire, okay, so obviously here we should get a distance D is equal to a distance of 25 centimeter. Now we will work out, okay. Now for opposite currents, the neutral point should be outside as theoretically said. Obviously the options is D is the right answer. Without doing any calculation, by a simple knowledge of this one, we can work out. If the currents are parallel, then the neutral point is between the two conductors. Here the currents are anti-parallel, therefore the neutral point should be outside. And one more thing, since we have to calculate what is the distance from the conductor carrying a larger current. Since it is a larger current, distance should be greater than the separation. On that basis, answer is 25 centimeter. Okay, we will work out. Now we have a conductor here, it carries a current of 1 ampere, and another conductor carries a current of 200 milliamps, or it can be written as 0.2 amps. Now there is a point, it should be outside. The field due to 1 ampere current is very much greater than the field due to a 0.2 amps, and hence it should be right side of the two conductors as shown by that animated diagram there. Now I am choosing x as the distance of the point from the conductor carrying a current of 1 amp. Now we have the magnetic field due to a current carrying conductor, it is mu naught I divided by 2 pi r. Now here for the first conductor carrying a current of 1 amps, I will take the distance as x. Therefore B1 is equal to mu naught I1, its current is I1 divided by 2 pi x. And obviously what is B2 due to the another conductor which carries a current of 200 milliamps, it is B2 is equal to mu naught into I2 divided by 2 pi into x minus 0.2. Now these two fields should be cancel each other at the null point. Therefore B1 should be is equal to B2. Now comparing them and cancelling the terms, mu naught divided by 2 pi get cancels. I will get I1 is 1 amps, therefore 1 divided by x, it should be is equal to I2 is 200 milliamps or 0.2 divided by x minus 0.2. Okay, so cross multiplying x minus 0.2 is equal to 0.2 x. Now further simplification leads to 0.8x is equal to 0.2. Therefore x is equal to 1 by 4. 0.2 divided by 0.8, that is 1 divided by 4. X should be 1 divided by 4. Therefore x is equal to 0.25 meter, because we have converted everything is in meters. So therefore it is 25 centimeter. Hence D is the right answer here. Okay. Now next problem. Two parallel conductors A and B separated by a distance of 5 centimeter carry electric currents of 6 amps and 2 amps in the same direction. They are carrying the current in 6 and 2 amps. the point between A and B where the magnetic field is 0. Now this problem is similar to that of the previous one, but the only thing is currents are parallel. Since the currents are parallel, the null point should be, or the point at which the field is 0 should be between the two conductors. Should remember this point. The options: 0.25 centimeter from B, 1 centimeter from B, 1.25 centimeter from B, and 3.75 centimeter from B. Now in the answer they have asked the distance from the conductor B, that is second conductor. Now let me choose the distance of the null point from the second conductor as x. Okay. Now we have the expression for the parallel conductor. B is equal to mu naught I divided by 2 pi r. Okay. For the second conductor, BB is equal to mu naught I B divided by 2 pi x. Let that point is at a distance x from the second conductor, that is B. And for the first conductor, the same formula becomes BA is equal to mu naught IA divided by 2 pi. The distance becomes phi minus x, because phi is the distance of separation between the two conductors. Now these two are equal at a certain point, therefore BA is equal to BB. Equating them, mu naught IA divided by 2 pi into phi minus x is equal to mu naught IB divided by 2 pi into x. Mu naught by 2 pi get cancels. IA is given and IB is given. IA is 6. So 6 divided by 5 minus x is equal to IB is given, that is 2 divided by x. Now cross multiplying, 6x is equal to 5 2 so 10 minus 2x. 10 minus 2x. Now simplifying, 6x plus 8x, it is 6x plus 2x, it is 8x is equal to 10. Therefore x is equal to 8x is equal to 10. Therefore x is equal to 10 by 8. It is 1.25. Now it is 1.25 centimeter from the point B. Obviously C is the right answer. Now here we have not converted the distance into meter, because in both the cases it gets cancels out. Okay. Now we can solve this problem in a shortcut by using a shortcut method. Now since the null point is, since the two currents are parallel, the null point is between the two conductors. So therefore we have the magnetic field B is equal to mu naught I divided by 2 pi r. From this relation, I proportional to r, because the magnetic fields are equal. Therefore we have to divide the distance in the ratio of the currents. Okay, the currents are in the ratio I is equal to I1 plus I2. Now I1 is 6, I2 is 2, therefore I1 6 plus 2, it is 8 amps. Now we have to calculate what is the point from A or B. Now distance from point B, because we have to calculate, because answer is given with respect to B. Distance from the second conductor B is equal to current flowing through the second conductor I2 divided by the total current into the distance. This is simple method. Okay. So current flowing through the second conductor, it is 2 amps divided by 8 into 5. Therefore it is 5 by 4, it is 1.25 centimeter from the second conductor B. Therefore C is the right answer. Now this is the shortcut method. Okay. Next problem. A proton is projected with a velocity of 10 to the power of 7 meter per second at right angles to a uniform magnetic field of 100 millitesla. The time in seconds taken by the proton to traverse 90-degree arc. We have to calculate what is the time taken to traverse a 90-degree arc, and given m mass of the proton, it is 1.65 into 10 raised to minus 27 kg, and charge is 1.6 into 10 to the power of minus 19 coulomb. The options are 0.81 into 10 raised to minus 7, 1.62 into 10 raised to minus 7, 2.43 into 10 raised to minus 7, and 3.24 into 10 raised to minus 7. Look at the option. Now time period T is given by 2 pi m divided by qb. 2 pi m divided by qb, it is the general formula. Since it is traversing 1/4 of the circular path, that is 90 degree, therefore we have to multiply it by theta by 2 pi. We know that time period in a circular motion is given by 2 pi m by qb, but we have to multiply it with theta by 2 pi. Now theta is 90 degree, therefore substitute theta is equal to pi by 2. So substituting the values, 2 pi into m value is given 1.65 into 10 raised to minus 27. The denominator charge is given 1.6 into 10 raised to minus 19 into the magnetic field is given 100 millitesla, therefore 100 into 10 raised to minus 3 into theta is pi by 2 divided by 2 pi. Pi get cancels and 2 get cancels. In the numerator we are having pi. If you substitute the value of pi, 3.14. In the denominator we have 1.6 into 10 raised to minus 19 and 2, that is 3.2. Now that 3.14 or 3 divided by 3.2 almost get, if I assume that it is cancelled, the remaining is 1.65. Therefore answer should contain 1.6 something value. Therefore on that basis B is the right answer. Therefore we will get 1.62 into 10 raised to minus 7 seconds. Therefore B is the right answer. Like this we can easily simplify this one without using the calculator. Move on to the next problem. Two identical conducting wires AOB and COD are placed at right angles to each other. The wire AOB carries a current I1 and COD carries a current I2. The magnetic field at a point lying at a distance d from the intersection of the two conductors O in a direction perpendicular to the plane of the wire AOB and COD will be given by options A u0 into I1 square plus I2 square divided by 2 pi d, B u0 into root of I1 square plus I2 square d divided by 2 pi, C u0 into square root of I1 square plus I2 square divided by 2 pi d, and D u0 into I1 plus I2 divided by 2 pi d. Now look at the diagram. Now we have two conductors, one conductor AOB which carries a current in one direction and another conductor COD which is carrying the current in the opposite direction. Now AOB current, it is flowing from top to the bottom if I assume, and COD current is carrying the current in another direction. There is some point P which is perpendicular to both the conductors. Now at that point we have to calculate the magnetic field. The magnetic field due to, okay, this is D is the distance from the two center of intersection of the two conductors. Now we have to calculate the expression for the case of a conductor. Magnetic field B is given by u0 I divided by 2 pi r. For the first conductor, B1 is equal to u0 I1 divided by 2 pi d. For the second conductor, B2 is equal to u0 I2 divided by 2 pi d. Now carefully look here. The direction of these two magnetic fields are mutually perpendicular to each other at the point P. Okay, clear? Since the two conductors are mutually perpendicular, the direction of the magnetic fields from these two conductors at the point B are mutually perpendicular. B1 perpendicular to B2. Now we have to calculate the resultant. Now the resultant is equal to square root of B1 square plus B2 square plus 2B1 B2 cos theta. Now theta is the angle between B1 and B2. As we have told, these two are perpendicular. Therefore the third term becomes 0. Therefore B is equal to square root of B1 square plus B2 square. B1 square is u0 I1 divided by 2 pi d square plus u0 I2 divided by 2 pi d square. Now here u0 divided by 2 pi d is common. If we take it out, we get the square root of I1 square plus I2 square. So this is the answer. B is equal to u0 into I1 square plus I2 square divided by 2 pi d. Hence C is the right answer here. Next problem. A current I flows along the length of an infinite, long, straight, thin parallel pipe. Then the magnetic field at all points inside the pipe is same but not zero. The magnetic field is zero only on the axis of the pipe. The magnetic field is different at different points inside the pipe. The magnetic field at any point inside the pipe is zero. Now we have a pipe. The current is flowing on the surface of the pipe. By using Ampere's circuit law, B into L is equal to mu0 into IE. What is IE? It is the current enclosed. If you take any point inside and draw an Amperian loop inside the pipe, it will not enclose any current. Therefore, current enclosed inside the pipe is 0. Obviously, according to ampere circuit law, the magnetic field at any point inside the pipe is 0. D should be the right answer. So, ampere circuit law, B dot L is equal to mu naught into IE. Since IE is 0 here, we get D is the right answer. Next problem. A long straight wire of radius A carries a steady current I. The current is uniformly distributed across its cross section. The ratio of the magnetic field at A by 2 and 2A. Options: A 1 by 2, B 1 by 4, C 4 and D it is 1. Now they have given a wire which is a current carrying a current, and this has a uniform cross section. That meaning is current is uniformly distributed. Now here we have to calculate what is the magnetic field at a distance of A by 2, that is the inside the conductor, and at a distance of 2A. Now due to a circular wire, due to a straight wire, the magnetic field B is given by mu naught I divided by 2 pi r. Let me take the first case at a distance of 2A. If I take B1 as at a distance of 2A, so B1 is equal to mu naught into I divided by 2 pi into 2A. Now that is mu naught I divided by 4 pi A. Now the second case is the point is inside the conductor. Therefore inside the conductor the current has to be decreased, because according to the ampere circuit law, if you draw a loop at A by 2, it encloses a lesser amount of current. First we have to work out what is the current enclosed and then substitute in the value. Now for the second case, formula is mu naught IE, current enclosed here. In the previous case, at the outside point, if you draw an Amperian loop, it encloses entire current which is flowing through the wire. But in the second case, the point is inside. If you draw an Amperian loop, it encloses only a small portion of the current. That we have to first work out what is the current enclosed. For that concept, we have to make use of the current density should be a constant. What is current density? So J is equal to current per area. That should be a constant. Now based on that concept, the charge density, current density or charge density should be the same. That is I by A is equal to IE by AE. I, the total current flowing, A, the total area of cross section of the wire, and IE, the current enclosed, that we have to calculate, and AE, area enclosed by that Amperian loop. If you consider this one, now I divided by total area pi into A square, because A is the radius, and is equal to IE divided by pi into, what is the radius here? A by 2 whole square. Now upon simplification, therefore IE is equal to I by 4. Therefore it only encloses 1/4 of the total current. Now if you substitute this one in the expression for V2, we get V2 is equal to mu naught into I divided by 4 divided by 2 pi into A by 2. Now simplifying this one, we get mu naught into I divided by 4 pi A. Now B1 is also mu naught into I divided by 4 pi A. B2 is also mu naught into I divided by 4 pi A. If you take the ratios, it becomes 1. Hence D is the right answer here.